Good. Okay, so I'm Charles Gould from the University of Pittsburgh. Today, I want to give a little bit of a story of, well, my involvement and the overall efforts in debunking an experiment which claimed the observation of chiral Majorana fermions in quantum anomalous Hall insulator superconducting structures. Just a few words of background, because this paper is probably a little bit outside the field of expertise of some of the people here. The basic idea is based on this theory paper is fine, where if you have a quantum anomalous Hall edge channel, which carries electrons around the edge of a topological magnetic insulator, and you induce superconductivity in this topological insulator, you split this electron carrying edge states into two Majorana carrying edge states with the two different flavors of Majorana. Yeah, beautiful theory paper. And the paper, which is our topic today, this is a figure from it, is an attempt to experimentally show this. Basically, this is from the paper. Is this later? Yes. So each of these is now a Majorana edge state. So it's an green and pink are a single electron edge state, which has been split into two. For visualization. And the idea is that under the superconductor, you can really split it into two. So you can create a situation where half of an edge state is reflected and half is transmitted. So you would have a situation where you can have half eclipsing of conductance quantization. This is, again, from the paper. This is a schematic of the device. This is a control, just normal quantum anomalous Hall device. And then this is a strip of quantum anomalous Hall insulator material covered with a bit of superconductor to allow this experiment. This is a picture of the device. The picture and the schematic are a bit misleading, because if I take this picture, put it into Chiral Draw, and enhance the image, I find out this is actually a Hall bar as well, with the strip of superconductor on top. This will be important for the debunking story later. Nominally, this would not be important if there was nothing else going on. Okay, the basic experiment, sorry about the German, I actually grabbed this from, this is a slide prepared by an undergrad in a journal club I give in the 6th semester. But this is just, again, the schematics from the paper and just the students sketching out what is expected to be seen. At high magnetic fields, you have a single edge state because the superconductivity is dead. So you've got a conductance of one klitzing. And then at intermediate fields, when the superconductor turns on, you get a 1/2 plateau. And it is this 1/2 plateau, which is the evidence of the chiral Majorana. So this is schematic drawn by one of my undergrads based on their figures. And this is the paper where you see their data, and you see indeed this 1/2 plateau, proving the chiral Majorana. Everyone's happy. Okay, so that's the paper. Now, immediately when it came out, this got my spider sense tinkling, not only mine, several people in the community, because from a theory point of view, fine, I have a topological insulator. I want to induce superconductivity in it. I have a Hamiltonian, and I had some term to the Hamiltonian, which includes the superconducting gap. Poof, magic, I have a topological superconductor. From the experimental point of view, I need to induce the superconductivity. And now we can argue about the microscopics, but whatever the microscopics are, it means I've got a superconductor in proximity with my topological insulator. The wave function of the superconductivity interacts with the wave function in the topological insulator. This allows exchange of quantum information, but also exchange of energy, which means that it's going to allow equilibration. So here I have my superconductor. It's inducing my superconductivity, represented by this abstract circle. But it's also allowing equilibration of energy. And here, and here, and here. But the superconductor is an equipotential, surely. Even if it's just a normal metal, it's an equipotential compared to 25 kiloohms of a quantum Hall edge state, which means that I should be adding a shorting wire here to my Landauer-Bodecker diagram. So to my Kirchhoff's equation, which describes the edge states, I have to add two pieces of metal here, which short these edge states together. But if I do that, the entire schematic from 2 slides ago, which shows that 1/2 quantization to the 1 quantization, is no longer true. So this shouldn't work. The experiment worked. I saw the features in the experiment, but it shouldn't have. So yeah, this got me a little bit suspicious. And based on this, and based on rumors which I was hearing from certain colleagues who claimed that they had heard something but did not want to be too public about stuff, I felt the urge, together with Professor Mullenkamp, who I work in the same group as he, felt the urge to request raw data from the authors. They dodged for about 3 months. They basically ignored us. Eventually, we contacted other colleagues. We increased the pressure a little bit. Eventually, 3 months after our original request, which was in the fall of 2018, we got from the last author, from Kang Wang, an email containing some zip files which contained raw or primary data in the language of the first speaker. So data files with a lot of diagnostics data, a lot of extra data, so primary data. They were in a zip file. This is a screenshot of the directory of the zip file. When I open it, you see data collected, different files about 30 minutes apart. This is primary data on the time it was collected. Now, you'll notice that it was collected from June 1st to June 2nd. This is midnight. The internal metadata from the file allocation table in the files confirms these dates. They're actually off by 1 hour because of daylight saving time between the time these were put in the zip file and the time that the recording was done. This is the time the data was taken. It ended on 9 a.m., I believe it was, on June 2nd, which is a coincidence. It's the date the paper was submitted to Nature, Science, I'm sorry. Same day. Quite impressive. I don't have many PhD students who can write a paper in a day, but apparently they were able to. Even more impressive, these PhD students are really efficient, because while it was submitted on June 2, at 9:28 p.m. on June 1st, the first author circulated the paper containing this data to the authors for permission for submission. So he's really efficient. He's 12 hours before taking the data. Okay. Having said that, these are data files, primary data files, so they contain a lot of diagnostics. Now I will only mention the tip of the iceberg, because I could give a 10-hour talk, and just some people in the room have seen some of it. I have easily 10 hours of irregularities here. Some of them are, so you saw a bunch of files here. These are 18 columns of data with all the diagnostics and whatever, and a header which describes these 18 columns. That is true for all files except 127. 127 is 17 columns. The header still has 18, but the file actually has 17. Column 1, which is the timestamp, is missing. How can that happen? I assume someone opened the raw data file in origin or similar, and then pressed delete accidentally on a column, and then saved it again as raw data, which violates several things we teach our undergraduates. At random positioned files, there's missing values. If you ask Origin to plot this file automatically, it will not do it, because there's missing data points. The number of digits reported, for example, in the magnetic field or in the temperature sensor, changes during a single measurement sweep from 8 to 6 to 4 at random points in the file. Okay. With that said, the file does contain extra data. In particular, it contains not only R12, the two-terminal resistance of the device, but RXX. What do I mean? If we have a traditional hall bar, R12 is I pass current from one end to the other. I measure this voltage and this voltage. V divided by I is R. RXX is measuring this voltage between here and here, dividing by the current. Now, I have Landauer-Bodecker equations, so I can calculate what this should look like. R12, which is in the paper, should go from resistance of 1 to resistance of 2, conductance of a half, our XX goes from 0 to 1. Not true. This is the data from the paper, the blue. It does what it's supposed to. The red does not. There is no model, so this is calculated without assuming my short. If I assume my short, then this curve is fairly close to what I expect, except that this line should be at 1, not at 1.2. This curve, then I cannot explain. So these two curves are mutually inconsistent with any edge take picture I can come up with. Moreover, these are inconsistent with the laws of thermodynamics because here, Rxx is above R12, which is me saying the middle part of the wire is larger resistance than the entire length of the wire. Obvious nonsense. So I thought this deserved an explanation. So I sent this slide back to Kang Wang. Please explain. No accusation, just I noticed this in your data and I would like an explanation. I got this reply back at this time. So in December of 2018. First of all, there's no theoretical prediction for Rxx. Yes, there is. They're called Kirchhoff's laws. I know how to apply Kirchhoff's laws when you give me an edge state diagram. Actually, they're called Landauer-Bodecker in the context of edge states, but they're the same as Kirchhoff's laws. But the most important sentence is, importantly, Rxx data was not used in the publication. So that can be addressed separately. So flat out, I'm ignoring inconvenient results. This email is nevertheless important because he confirms, unwisely, but he confirms that I'm correct, that this is the Rxx data belonging to the sample and it's not some other sample or whatever, because he's not telling me, oh, no, you misunderstood, that's something else. He's trying to argue away that there's nothing wrong. Okay, looking at more of the data, the blue curve is from the paper. It plots the in-phase signal on the lock-in. Lock-ins often measure quadrature, so in-plane and out-of-place signal. The out-of-plane is conveniently in the data file. Total resistance should be given by the square root of the sum of the in-plane plus the out-of-plane. That's the red curve. Doesn't fit the predictions at all. The blue curves did. But you can also see here, these are the gaps in the data which I was talking about. Here there's a bit of data missing. Here there's a jump in the data because some value change jumps spontaneously. So when I look at the out-of-plane signal, it makes no sense. Yeah. So out of phase, what did I say? Plane? Out of phase, I'm sorry. When I look at the out-of-phase signal, it makes no sense. Good. This is for one of the curves. This is the field sweep just versus time. So normally when I do a measurement, I sweep my magnetic field at some constant rate from -2 Tesla or +2 Tesla to -0.5 Tesla. Not here. Here, this is just time. We're sweeping constant rate. Okay, now we're parking for some time. Maybe something went wrong, whatever. But now we start again, and now we start, and this is where the interesting features are. We start, accelerating, slowing down, going at different rates. Some of these are not even straight lines. If you zoom in, they're curved. So this looks like stuff we're spliced together. This left figure is from a presentation PowerPoint file. This is the name of the PowerPoint file, which the first author presented in April 29, 2016, so 2 months before the paper. This is data at 350 Kelvin. So this is above 350 millikelvin. The June 2 data is the one between 350 and low temperatures and base temperature. Nevertheless, if you look at this and the data from the paper, this is the same data set. You can see these little noise features are over here. This is the same data set. However, this point was above 7.5, and now it's below 7.5. And this point was at 2,800 Ersteds, and now it's at 2,500 Ersteds. So they've rescaled both the X and the Y axes, apparently for fun, because this or this is completely equivalent. It's not like this is a better result than this, but apparently just for fun, they rescale the data. It's a hobby of theirs, I guess. Other rescaling, ConMat archive, paper, and characterization of the superconducting strip itself. Superconducting stops at 4.5, stops at 7. The extracted critical fields, because they extracted it differently, get exactly the same value, which is convenient because it's the slope of this line which actually enters into matching the theory. So that's convenient. Okay. Now, that's basically what I had to show about this paper. Again, it's just the tip of the iceberg. And now a few comments about what surprised me the most. So as I said, I run a journal club where we present this paper at the last paper of the year after we've presented a lot of papers where we hope people see how science should be reported. We use this example as a to show that students must be vigilant. By this time in the presentation, the common reaction I've gotten is that students are telling me, if we did any of this, we would have been expelled by now. Which is true, they would have been. What surprised me is how weak, sorry, I misspelled, how weak the guardrails are actually in real life as opposed to student life. So this paper has been retracted. So this did work, but it took 4 years after the discovery of the fraud, meaning after it was discovered that the paper was circulated before the data was acquired, according to the authors themselves. It took another 4 years before the retraction was finalized, and the retraction is still not agreed upon by most of the authors, only by a few. Perhaps I was naive, but I was expecting this to be a 4-day or maximum 4-week process, not a 4-year process. The other thing, and this was touched upon by the first author, by the first speaker, sorry, today, they did eventually put also what they claim to be raw data in a repository. The raw data in the repository, though, was not raw data. It was not the one which Kang Wang sent me, but it was a data graph of where are the pixels, to the point that the raw data includes the offset for clarity. We were not satisfied with this raw data. We approached science. We asked science if anything could be done about it, because if you publish in Science, you agree to make your raw data publicly available. And we were basically told that the authors are responsible for deciding what the definition of raw data is. So as long as they say it's raw data, they've satisfied the regulations. This is also a comment you made. We should have a stricter definition of raw data as a condition for publishing, I think, is an important takeaway. We were also very, very surprised and curious. This is something else we've discussed in this journal club. We've never come up with an explanation as to why science had this policy, because our first reaction when it was not being retracted quickly is we wanted to write a comment. I can write a comment where I can say, you know, Rxx is larger than R12, question mark. But we were prevented from doing so because science has some policy that you can only write on comments which are comments on papers which are less than 3 months old. How that is beneficial for promoting science and open discussion is a mystery to me. Instead, something rather groundbreaking happened. So science, basically accepted this paper. This is, I'm calling it groundbreaking because as far as I'm aware, this is the first time that science actually accepted a negative result paper. So instead of a comment, we basically published a paper together with colleagues from 200 miles away from Penn State, which basically says, there's a reproducibility problem here. We cannot reproduce it. This was, however, a scientific paper, not a comment. So there was no clear statement why we cannot reproduce. I mean, we know why we cannot reproduce it. We don't say that in this paper because it's a scientific paper. We just redo the experiment, doing everything they've done, and show we get different results. Okay, so that was my surprise on the journal side, that the journal does not, in particular, relating to how quickly they can act and to how strict they can be about data. I was surprised that they don't have more tools at their disposal that they do. My biggest surprise and shocked and disillusionment is these are all authors from a pretty well-known place. These are from University of California. This is not, some backwater university which no one has ever heard of. Sorry, not these authors, but the authors on the first paper. These authors are from Pittsburgh and Penn State, which also are not backwater places, but the other authors on the first paper are from the University of California. Everything I've just shown you and much, much more, a much longer version, was sent to the University of California, to UCLA, where the first and last author are employed, or were employed at the time of publication. Last is still, first is no longer. And to the University of Irvine, where the measurements were done. But technically, we sent it to UCLA. UCLA forwarded it to UC Irvine, where the measurements were done. After about 3 months and a few follow-up emails, we finally got a reply through the Vice Chancellor for Research at the University of Irvine. He looked at all of this data, looked at everything, and engaged a Dr. Roger Wakimoto, who is Vice Chancellor of Research at UCLA. Yes, okay. Discussed with him, engaged Dr. McWilliams, who is an expert, allegedly expert in the field. They looked at everything we sent and concluded that although the allegations are reasonable and specific, potential evidence of research misconduct cannot be identified at this time, and therefore an inquiry is not warranted at this time. So not only does this not convince him of wrongdoing, this does not convince him that there's any questions to be asked. And this, frankly, left me completely speechless, which is why I will stop now.
Ross, questions? Yes.
So thank you very much. This is my home institution. So there have been colleagues who have posed questions to our Vice Chancellor of Research. I know that conferences I go to, I get asked about, well, what does UCLA, what actions are they taking, et cetera. I guess the question is, what would it take for the universities to acquire a little bit more sense of responsibility when issues like this come up? Because I think this is what this letter documents, is that, this is not our problem.
I agree. I think that's the question. And I do not have an answer, but I would hope that maybe we can, during this conference, talk about going towards that, because I agree that's exactly what this reads like to me.
If I may ask, and if you want to disclose, but are you undertaking or considering further steps, or are you leaving it at this? And
we're undecided.
And can you comment on why? Like, I'm interested in your motives, or why you are undecided to the point that you want to.
Yeah, so this already is representing this, and all the is representing somewheres in the neighborhood of 2 years of PhD student time, and we keep running up against brick walls like this. It's unclear to me what more I can do than show documented forensic proof that the data was acquired after the paper was circulated to get a reaction. If that doesn't get a reaction, I mean, I could convince my grandmother, if she was alive, that this is a problem. That if that does not get a reaction, it's unclear to me what the next step could be.
Yeah, I think that's part of a bigger problem that we, or maybe not we, as I don't know, as a mankind, are approaching this situation from legal point of view, like 12 Angry Men. So if there's any shred of doubt, that it should be interpreted in favor of the accused. That's not the case in science, and this legal-like approach or IRS-like approach is not right. IRS audits 0.2% of their tax returns, and their budget has just recently exploded to $90 billion. We cannot do that with any paper. There should be a venue for publish this type of concerns. You know, it has to be reviewed by independent referees, any other scientific publication, but the attitude, and I'm talking to whatever representative publishing board are here, the attitude, well, this is the comment of a paper, or even this is a comment on papers that had been withdrawn, is not the argument. It's a scientific result. People invested a lot of effort in obtaining this scientific result, and it has to be publishable. It has to be publishable more than, of course, Condensed is great, archive is great, but it has to be publishable. The people who spend time, whatever students involved, should have credit for the publication. And then the people will be, people involved in that, they will face the situation that community, broad community knows about this problem. Then they will have to respond with whatever they have. And it's not the campus police issue. Well, okay, that's what I want to say.
Want to reply to this?
No, I agree.
Thank you. So I also wanted to make a quick comment. I think universities and, VPs for research and so on are probably much more responsive to measures taken by grant agencies. That's where.
We were told we do not have standing.
Right.
Just a quick comment, as I was very surprised by this result here, because typically universities have a policy, which is written, Caltech, all these, they have the policies. And you always have an inquiry to determine if there's grounds for investigation. All misconduct cases where it's classical misconduct, Title IX. And so one of the things we might do with this workshop is in one of the subgroups is, let's talk about a general policy that universities can reach into. So.
Yeah, but I was also confused because it is my understanding that UCLA does have such a policy. But then when confronted with a case, maybe the policy is just a suggestion. I don't know.
If they agree, they have to take administrative measures, firing, dealing with tenure, all sorts of things, also this. I don't think that's real answer. The real answer is the public exposure. And then, by the way, speaking about funding, yes, that's right. And when people who will be referring their next proposal will be aware, because it's been published in a widely circulated journal, that there is a problem that will affect their comments onto this proposal. Again, I don't think it's university administration has to act after it was established, so whatever, but it's not our problem. Our problem is that these people are known to do improper things. And what happens with them, I know I'm not bloodthirsty. I don't care what happens with them.
Just a small comment. Even when you get the attention of the university, in the case of Diaz, they had 3 internal committees look at him and it said there was nothing wrong, right? So 3 times they looked at him. And so even if you get their attention, it's not clear that justice will be served.
So I think there was another set of work, right, involved with Microsoft, where I think in that case there was an external group of people put together. So the problem here is that it's internal.
Wait, the problem here is that we cannot even get to an inquiry. This is internally squashed.
I just want to mention, I think it is our problem, Igor, because there's students involved, right? This is the broader scientific community. If you look at the case we know about Diaz and Salamat, there was a lot of fallout with students, and we can't just throw them under the bus. So we have to get involved at this level as well.
Thanks once again, Charles.